Now, it's a real pleasure today to introduce Bob Wasson. Bob is a geomorphologist, and I actually really love it when we get some of this type of stuff. Some of the allied sciences are the types of sciences that are not necessarily right in the realm of ecology, environment, evolution, all that type of thing. So it's great to stretch our boundaries a little bit. Bob grew up in Sydney. He went to the University of Sydney and then to Macquarie University for his PhD. He's held positions with CSIRO. Well, he did a postdoc in New Zealand. He's held positions with CSIRO, long time positions, number of positions with ANU, and also with Charles Darwin University. And now he's he went to Singapore to be stationed at the National University of Singapore, another really good university, for several years before retiring. But fortunately, he hasn't completely stopped doing interesting things, and we're really glad to have him today talking to us about rainforest to oil palm, and I'll let him tell you about the rest of that title. So thank you very much, Bob.
Thanks very much, Bill, for that introduction, and thank you all for coming. Who knows who's on Zoom? It could be quite a surprise. I'd like to begin by acknowledging the traditional owners of this country, the Irukandji people, and pay my respects to their elders past, present, and emerging. I'd also like to pay my respects to Yoko for her organisational skills, which are quite exemplary. Thank you, Yoko, very much indeed. This is a piece of work that was done a number of years ago. I'm gradually working my way through the unfinished business, and my strategy here is to promise to do a seminar, force myself to write a PowerPoint in far too much detail, so then I turn it into a paper. So the amount of detail in here is too large. I will skip through a lot of it and just give you the take-home messages, I hope. It was also an area just across the straits from Singapore where I used to take undergraduate students for field trips. So I had some forced labour, volunteer labour. So this is the team, excuse me. I've set this in the context of ecosystem services, where the replacement of rainforest by agriculture is what is known as a provisioning service, and it's driven by demand for products particularly. Because it's worth remembering that the original rainforest in this area, lowland dipterocarp forest, actually provided services to the indigenous people, the orang asli. And I think it's not, so ecosystem services shouldn't just be considered within the framework of the modern world. Erosion and sediment transport control, or at least mitigation, is a regulating or maintenance service to maintain a natural resource. And so we can see that the benefits of this are to maintain the soil resource for agricultural or other purposes, below ground biodiversity, which is immense, and of course downstream water quality. I'm not going to talk about nutrient loss and organic matter loss, but that is also an important part of the story, not just sediment production. So I want to focus particularly on soil loss and to some degree water quality impacts of oil palm plantations. I think you'd probably agree from this photograph that the water quality impact is not all that wonderful. But I want to step back for a few moments and think about the soil resource globally. This is a compilation of data put together by David Montgomery some years ago now, published in PNAS. David is a geomorphologist, University of Washington. And his conclusion is from these data, and he's expressed the units of erosion are perhaps to you a bit odd. They're in millimeters per year of lowering. And his conclusion is that conventional agriculture produces about 90 times the erosion rate compared to soil production. In other words, this soil production cannot keep up with the erosion rate globally. Conservation agriculture is a lot better, but the ratio is 5 times. So it's not 0 or 1. His calculation is that in many parts of the world, the soil will be completely gone in about 500 years. In other cases, a few millennia. This is something that came up in the conversation with Paul's seminar about the sustainability of agriculture into the distant future. How are we going to get on when we run out of soil, if we run out of soil? There are other ways around this problem to some degree, but it is a serious issue. We talk about climate change quite properly. We talk about biodiversity loss quite properly. Soils seem to have fallen off the agenda to some degree. And I think that's quite a mistake. A recent piece of work by Belthier et al. On those rivers of the world where suspended sediment, the finest particles in the rivers, are increasing, the fluxes are increasing. And they've apportioned those rivers to particular, what they consider to be land use causes. Now, there's two 17% here, it's maybe coincidence. They say that about 17% of the world's rivers between 1984 and 2021, for which they have remote sensing data, that the suspended sediment flux is increasing by about 41%. The increase in 17% of those 17% is because of oil palm plantations, they claim. And you can see in the table what the others are. General deforestation. Their categories are a little bit odd, but there you are, is 46%. But what are the processes? If these figures are an accurate representation of reality, what are the processes by which oil palm plantations are increasing this suspended sediment flux? We just now look at some of the data, and it's pretty sparse. Erosion rates from forest to oil palm in Peninsular Malaysia. And the increase is something between 1.5 and 78 times at the plot scale. In small catchments, it's up to 53 times. In other words, when land goes from rainforest to oil palm, you get an increase of up to 78 or up to 53 times, depending upon the scale of the measurement. And you can see from that little graph that slope is an important variable in that increase. Here, the erosion rate is in tons per square kilometre per year, and the slope is in percent, not in degrees. And you can see that slope is an important variable, but there are others that play a role. So let's just think about the story of rubber and oil palm in Peninsular Malaysia. From the 1780s, the Europeans, the British particularly, introduced, along with the Chinese had actually introduced a lot of these crops earlier. There were a whole range of crops, but the commercial cropping began seriously at about that time. Rubber was introduced and established quite widely by about 1913. Oil palm planted from 1917 and increased quite rapidly. And now the current situation is about 20% of Peninsular Malaysia is under oil palm, amounting to about 12% of global production. It's quite an important crop economically, and for a lot of people depending upon it for their livelihoods. But it's in a biodiversity hotspot. And the map on the lower right shows various kinds of forests. We won't dwell on it. About 15% of forest cover in Malaysia is primary. So there's forest, but an awful lot of secondary forest. So one wonders if there is more for oil palm in the lowland forests yet to be developed. Just a quick sketch of this, just because I'll be referring to some of these phenomena later. The key erosion types that I want to stress are the sheet erosion, the right-hand side and the left-hand panel, which is really just the removal of the surface part of the soil. And then gully erosion, of course, which is pretty self-evident. Rills are really, in a way, small gullies. And interestingly, inside the gullies or the incisions that are in this particular site that I'll describe in a minute, there are landslides. But I just thought I'd include that there for completeness. You'd also to think a little bit about erosion control and the catchment system state. The one on the left-hand side is what I suspect this field site that we looked at looked like during before disturbance, before clearing of the forest. In other words, it was a shallow channel in a swampy valley floor, vegetation all around, and the dominant process by which sediment got into that river was by sheet erosion off the surface of the soil. There were probably no gullies, no landslides, just a bit of sheeting, and very low rates of sheet erosion. On the right, you see an incision. Now, for some of us working in Australia, and Jack Coaching may well be on the Zoom, you'd say that's the dominant source of sediment. Whenever you get a gully, it is the dominant source of sediment. Well, not so here. Now, the Oil Palm Planters Association in Malaysia, I think I've got the name wrong, but that's what they do. They've gone to some lengths to document and even mandate certain erosion control measures. The photograph there shows palm fronds chopped off the trees, laid out so as to catch runoff and catch sediment. They also use empty fruit bunches in a similar way. There's a little bit of cover crop there as well. When the trees are first planted, they put in a cover crop to try to reduce the area of bare soil. They should not plant on slopes more than 20 degrees, not percent, but they do. Terracing on the steeper slopes, they put in sediment traps. They put in soakways along roadsides to limit runoff, and they try to limit heavy machinery in certain areas. They've also, in the area we worked in, put palm fronds along the channel margins in an attempt to control erosion there. In rubber plantations, there are very few rubber plantations left in Malaysia to go and see what's happening. But litter maintenance and cover crops seem to have been quite important. The assumption in all of this erosion control is that sheet erosion dominates. Now, the site I want to talk about is LADANG SEDENAK. We take a whole of system approach, a whole of catchment approach. It's only a sediment budget, not a nutrient or carbon or pollutant budget. A sediment budget quantifies the sources, the sinks, and the losses from the catchment, ideally through time. And for reasons I'll explain in a minute, we have a 16,000-year record. Now, on the right-hand side is the most remarkable piece of work from Stan Trimble from the United States. That is, he was very lucky to have a huge amount of data from this area called Coon Creek in one of the Midwestern states. I can't remember offhand which one. We can't match that. It's just phenomenally detailed. I've already mentioned a 16,000-year record. Why on earth would we go that far back? I argue in virtually all the work I do that a historical approach is essential to understand how the present state came to be. Ideally, we would have a time-structured sediment budget to see how it's changed through time. Provides us with insights into the future. That is what we have attempted. Okay, here's the SEDENAK site. You can see him just near a little town called Kulai. And right on the left-hand map, oh, I can use this magic machine. Well, I don't know. Oh, it's that. No, yes, it is that. Down here is the sub-catchment, tiny, tiny little sub-catchment in which the work is done. This map is based upon aerial photographs in the 1950s. And remember that rubber was planted in from about 1917 and oil palm from about 1968. So this map shows the distribution of rubber in the dark grey colour. But institutionalized erosion control really didn't start until 2005. So we don't really know what was going on during the period of rubber plantations or the early period of oil palm. The sub-catchment, as I said, is quite small, quite deliberately so, to maintain some sense of order, so shall we say. Tiny area, relief only 50 metres. One of the interesting characteristics of this, as you can see, three little streams. The valley heads are amphitheatre shaped, which implies groundwater seepage and groundwater control of that structure. The bedrock is uniformly granite, the soil is the Rengan series, and the FAO terminology is in brackets, one of those hideous soil descriptors. And the original vegetation, as best we can judge, lowland forest, and quite a wet location. This is not from the site, but this is what amphitheatre-shaped valleys look like. It is almost certainly a result of groundwater seepage, probably another source of sediment, but we weren't able to quantify it. Now let's have a look at the valley floor. The idea of looking at the valley floor in some, well, initially just to get an idea of the age at the base of the sediments in the valley floor, was to calculate the sediment storage in this particular part of the catchment. In other words, if you know the age at the base, you can calculate, and you know the volume and therefore and the mass, you can calculate the storage rate and the total storage. But what turned out, we got a bit more information than that, and which I will now divert to for a little while. You can see the here is the oldest date. These are luminescent dates thereof, by the way, given our previous conversation. Let's call it 16,000 years. Interestingly, and I will just quickly shoot through this because I don't want to spend too long on this particular topic, there are various sediments in this, and we have pollen from some of these sediments, which give us an idea of what has been going on through that 16,000 year period. The bottom line is, 16,000 years ago, there was no rainforest. It was a forest grassland. And we know that also from another site. Whoops. That's, as I said, that's the photograph I showed earlier. From about 16,000 to 8,000 years ago, swampy floor with forest grassland, then rainforest, with charcoal suggesting some human activity. Then a slightly less swampy valley floor, and then, of course, from about 1917, forest clearance. Not a very good photograph, which shows basically the sort of sediments we're looking at. We'll press on. At Nisun in Singapore, we have a much better record of pollen, etc., which shows this, essentially the same sequence. This period, you can see here the poaceae, the grass pollen, very high and then dropping down. And the rainforest picks up from around about, so it's constant approximately from about 7,000 years. So there was this forest treed grassland, which other people, including Michael Bird from this university and others, have found in this region. And it's called the Savannah Corridor. And it runs through, whoops, I'll get this organized. Yeah, here's the Savannah Corridor, as mapped by Chris Verster, formerly of JCU, which is thought to have been the route by which people migrated through to Australia. Although, of course, this is much younger than the earliest dates for habitation of Australia. Of course, more recently, work has been done that shows that people were living in the rainforest quite happily, as they do now. And so as the only route of migration, that's an exaggeration. But the interesting thing is there was no rainforest at our LADANG SEDENAK site 16,000 years ago. It grew, it came in. That was the last phase of rainforest development. There must have been rainforest there earlier, but we don't have records to go that far back. So it's a dynamic system in which the vegetation is changing quite a lot. And then Europeans largely come along and start planting rubber, then oil palm. The valley floor was incised. In other words, it was cut down to form essentially a gully. And the question that arises, given what I said earlier, does that incision produce most of the sediment in the catchment? You see on the right-hand side there a diagram from a guy by the name of Portenga, who did his PhD on these things in southeastern Australia. I did some work on this as well. If you look at the top, you see a valley floor which has what is called a swampy meadow with kangaroos all around it. And then it cuts out in sizes, and a thing called post-settlement alluvium is deposited, otherwise known more generally these days as legacy sediment. And then to some degree, the thing stabilizes. And the incision occurs after European grazing starts. And you see at the bottom, on the left, the swampy meadow, valley floor, and on the right, the incision with the swampy meadow buried underneath post-settlement alluvium. A pretty good indication of the impact of us. So I'm not going to go through this. This is simply to tell you that we have methods. We applied methods to work out the components of the sediment budget as best we could. And here is the most recent version of the sediment budget. The intriguing thing about this site is there is no topsoil. The A horizon is completely gone. I had a team of students with shovels, and I'll show you a photograph of them in a minute. We went all over the place. We could not find a single example of the A horizon. So what we've done is to say, right, well, the A horizon in the Rengan series of soils has an average thickness of 18 centimeters. We have an area of 0.27 square kilometers. Multiply the two together, and what you end up with is something probably greater than 59,000 tons lost sometime during this time period. Probably more than that, because we don't know how much of the B horizon is gone. Landslides inside the gullies, they're measurable. The roads and trails actually, as in most forestry operations, do contribute considerable amounts of sediment. Channel incision, not so much. Colluvial storage, that's storage on the hill slopes, and some storage in the floodplain and in the channel. So the yield is something greater than 70,000 tonnes. Specific yield greater than or equal to 2,600. What was the pre-disturbance yield? Can we estimate that somehow? Well, there's a global relationship. Again, this guy Montgomery and his colleague Mark Brandon put this together some years ago, where they've got the erosion rate again in millimeters per year against mean local relief, the altitude difference. And they're little, I don't know what they are, squares. They're essentially low relief, tectonically stable, that is seismically stable areas. The other two are there just for comparison, the Brahmaputra and Ganga. From that, we get an estimate for LADANG SEDENAK of 0.01 millimeters per year. But there are enough measurements in Malaysian catchments to suggest that it's about 0.02. So we can compare the pre and the post-disturbance sediment budgets. We can calculate the storage in the pre-disturbance sediment budget from the dated sediments in the valley floor and masses, etc. And the soil erosion rate is going to be approximately equal to the soil formation rate. So in the pre-disturbance system. So we can make those sorts of comparisons. Interestingly, the bottom thing, the SDR, is the sediment delivery ratio. That's the proportion of sediment, the proportion of the total erosion that is lost from the system. So in both cases, it's about the same, 96 or so percent. Let's make that comparison a little easier to follow. The yield from pre to post disturbance is an increase of 112. The storage, incredibly, has increased by about 192 times, even though there's been incision. And the SDR is about the same. From a management perspective, the most important conclusions are sheet erosion is the main source of sediment, not the incision, not the gullies. That's despite the channels. And the storage mass increased after disturbance. mainly because of this legacy sediment that accumulated on the walls of the incision. So that's the major conclusion from a management perspective, that in fact the Oil Palm Plantation Society, Corporation, whatever it's called, has actually got for this particular area, has got the strategy right. Protect the surface of the soil. Because from our work in the site, the soil loss is about 120 times the soil formation rate. The soil will be completely gone in about 600 years. And it's sitting on bedrock, granite bedrock. But is it possible that there could be greater longevity with erosion control? Well, if you look at the other measurements for the area, the range for the time period over which soil would be completely gone range from 900 to 300 years, depending upon which data set you use. But these are all on slopes less than 5 degrees, which is about right for our case study. So the answer is yes and no. Depends upon which particular study you take into account. And so we need a bit more information about what the differences are between the 900 and 300 year catchments. The right-hand photograph shows sheet erosion plus the development of a rill. So the conclusions from this are the soil under oil palm is being mined. It's not being replaced at the rate of soil formation rate. Now, you could argue that that is true for agriculture generally. Again, we go back to the conversation we had with Paul. This is a mining operation. And the question is, how long can we slow it down? The conservation techniques, agricultural techniques, certainly do that. There may be others. I mean, Paul's talk was about sustainable agricultural systems from a variety of perspectives, not just soil loss. But how do we get the soil loss down to the soil formation rate? I'm not sure we can, but I'm really open to ideas about that. The current economic benefits of palm oil will not last forever. Okay, 600 years is quite a long time. And if you're an investor, you'll discount the future, and that doesn't really matter. But it matters for humanity in the future. If palm oil goes out of fashion, can the land be restored? When you consider, or to either rainforest or productive, some other form of agriculture. Well, the trouble is at SEDENAK, there's no topsoil. There's no lay horizon left. It'll come back, but it'll take a long time. And probably needs a particular sort of agriculture or sort of land management, I should say, to enable that. And if SEDENAK is typical of lowland plantations, and I'm not sure that it is, but I think it's close. Sheet erosion of soil is the major source of sediment. That's a very important conclusion, because it tells us if it is typical, it explains to some degree how those rivers, where the suspended sediment flux is going up, how that's being affected. What is the process by which soil erosion is affecting those rivers? It's sheet erosion, not channel erosion, not gully erosion, not landslides. That has significant management implications. Focus on controlling sheet erosion as best you can. In Australia, I became involved in this work in CSIRO. We showed in quite a few places in southeastern Australia, and now others have shown it up here, not in the wet tropics, but in the wet dry tropics, and in southwestern WA, and in the Kimberley, the gullies are the major source of sediment. Reservoirs are filling up with sediment because of gullies, not because of sheet erosion, although sheet erosion plays a part. So it's a very different story here from what appears to be the case in Malaysia. Now, the Oil Palm Association says don't plant on slopes greater than 20 degrees. In fact, this recent review in biological reviews suggests that it should be no more than 14 degrees. But there's a lot, particularly in Indonesia, there's a lot of planting on steeper land with terracing. But you know what, with terracing, if you don't have the terrace going back into the hill slope, it doesn't work. If you have it sloping outwards, it becomes a sediment source. And I've seen many terraces in Java that slope out. So there's been a major shift in the catchment system state, not from a sheet erosion dominated system to a channel erosion dominated system, but from one where the sheet erosion increase has been very significant, to the point where the rate of soil formation is overwhelmed by the erosion rate. But it can't be reversed quickly in fact, it can't be reversed, I would suggest, very much at all under the current agricultural regime. So we need, I mean, this is the sort of, I had in here originally more earth-shattering conclusions. Well, they're not really earth-shattering, are they? We need more studies of this whole of catchment type to check whether SEDENAK results apply. What we've got is a whole lot of plot studies of sheet erosion mainly, well, of sheet erosion and to some degree rill erosion, and also small catchment studies that are black boxes. We have oil palm or rainforest and outputs, but we don't know what's going on inside. What are the processes inside? Without that knowledge, I argue management is blind. You can't know what you're doing. But from these results, the take-home management message is apply the full range of erosion and sediment controls that are available to you. And certainly the people who are running the SEDENAK plantation were doing, I think, quite a reasonable job. And they were very cooperative with us, very helpful. But it may be necessary in some circumstances to consider retiring some of these plantations, on steeper land particularly. That may not be a very popular suggestion. And my acknowledgements. Here is the slave labour force from the National University of Singapore. You can see the only old white fella there is me. The guy here, Chua Chong Jun, one of the co-authors, a Malaysian working at NUS at the time, still does, and a whole lot of really, really good students, enthusiastic, hardworking, and of remarkably good cheer in hot and humid conditions, digging holes where I was saying, dig harder. And also for the assistance of University of Technology in Malaysia, which is based in Johor Bahru. And one of the authors of this paper is Zulkifli Yusop, who's an environmental engineer and has had students doing a lot of the plot studies, erosion plot studies and runoff studies. It reminds you, one thing I forgot to mention is that as soon as you clear the rainforest, not only do you increase erosion, you increase runoff rate. And the runoff rate goes up dramatically, which means that the erosion rate goes up because there's a lot of water moving across the landscape. Whereas under rainforest, the runoff rate is actually very low. And the erosion rate is also very low. So the ecosystem services provided by rainforest are quite remarkable. And as soon as we clear it, we remove a lot of those services, but we provide other services in the way of agriculture, etc. So that's all. I thank you very much for listening.